Good afternoon, viewers. Welcome to Jason online class tutorial. So I remain my humble self, JS, your physics teacher. This afternoon, we are moving completely into a new topic. Since last year, we have been dealing with a certain topic, which we tried to look. We finalized it last week, which is motion. Now, today, we are moving to work, energy, and power. I told those who were with me in my last class, if they want to ask any question concerning anything under the motion, so they can send me a message in my at any moment. So today now we are moving to a new topic. So work, so energy and power. So under this topic, we will be looking into work, energy, and power individual respectively. At the end of the topic, so at the end part of it, we'll be dealing with the both three aspects of it together. So, but today, we first start to look into work. So work, we look into the work. So we get to do some little calculations on work. Then we move on. So work, what is work? We all talk about work, we do this. But in physics, when we talk about work, you have to put some things together before you can do a work. So what is work? And when we talk about work, a work is the product of force and perpendicular distance in direction of the applied force. So when we talk about work, it's defined as the product of force and perpendicular distance in the direction of the applied force. Product of force, so, and the perpendicular distance in the direction of the applied force. That is what we refer to as force, work. Therefore, work, so will be equal to force times distance. Force times distance, according to the definition. So whereby we say that is the product of force and perpendicular distance in the direction of the applied force. Work will now be force times distance. Do not forget that our force is equal to mass times acceleration. So times what? Distance. Therefore, our W will be equal to ME times distance, which is what? ME times S. I don't need to explain this one further. We have been doing fundamental and derivative quantities and units. We did it together, and we can understand how we got to know, we arrived at ME times distance. So the symbol for distance is S. Now, our force is the same thing as mass times acceleration. That is the formula for calculating force, the mass and the acceleration. That is force times distance. We are dealing with work. So now the unit of work is in joules. Whatever we do with under it must end with joule. So I have to make it, I don't want to take a long time on this topic the way we waste much time on motion. That is, I just have to go through the key aspect of the topic. So as we move on to another part of it. So that is some brief you need to understand about work. So work is force and distance, a product of force, So, and the perpendicular distance in the direction of the what? Of the applied force. So what is said to be done when an object moves through a distance in the direction of the applied force? Before we can say that work is done, that means that so an object must move through a what? Through a distance in the direction of that applied force. That is when we can say that a work has been what? Has been done. So let us move to some, let's look into some examples of work. So work example. Okay. A filled drum of oil. A filled drum of oil of total mass 150 kg. Of total mass 150 kg. Rolls down from the floor. Rolls down from the floor. Rolls down from the floor of a lorry. Of a lorry 2.0 meter high. Of a lorry 2.0 meter high. So calculate the work done. Calculate the work done by gravity on the load. Calculate the work done by gravity on load. Now, we can try to bring out the parameters in the question. Parameters in the question. A filled drum of oil of total mass 150 kg. Our mass is equal to 150 kg. Rolls down from the floor of a lorry. So 2.0 meter high. So that should be our distance, which is S, 2.0 meters. Now, calculate the work done so by gravity on the load. So that is the question, and that is the parameter. Now, work done on the load, do not forget that our work is equal to MP times S. Force and distance. Our work is force and distance, and force is equal to mass acceleration times the distance. Now, according to the question, we were given mass, we were given distance. So our acceleration remains constant, which is what? 10 meters per second square. That's the constant of acceleration. So with that now, we can say work done is equal to our mass is 150 times 10 times 2. 150 times 10 times 2. Now, we can solve this by getting the right answer, 150 times 10. 0 times 0 will give us 0. 1 times 0, 0, 1 times 5, 5, 1 times 1. 1 times 0, 0, 1 times 5. Oh, sorry. 0 times 0, 0 times 5, 0, 0 times 1, 0. Sorry. So 1 times 0, 0, 1 times 5, 5, 1 times 1, 1. This will give us 0, 0, 5, 1. 1,500 times 2. That will give us 30,000. So that will be 30,000. This will go to 30,000, 3,000 joule. 3,000 joule. Don't forget that we can still convert our joule to kilojoule, kJ. So, but it depends if the question or how the question comes. If the question indicate that we should end our answer in kilojoule, so when you find your answer in joule, then you divide whatever you get by 1,000. So then you whatever you get will be in kilojoule. So that is 3,000 divided by 3 will give us 3 kJ. Either 3,000 or 3 kJ. Either 3,000 joule or 3 kJ. So we still arrive at the same answer. Now, I hope you get this. So that is as simple as that. So we look into another example under the work, but this time around, this one we deal with angle. So if there's any question concerning this, you all can drop me a message on my WhatsApp. Let's look into another example. So let's look into another example. Okay. This question, we have to clean this so that the space can contain the question and the solution, if possible. So with the help of a rope inclined with the help, this is another example, with the help of a rope inclined, with the help of a rope inclined at 30 degree, sorry, to the horizontal, a boy exerted a 20 Newton pulling force. 20 Newton pulling force at a desk and meant at a desk. And made it to move a distance and made it to move a distance. I made it to move a distance of 4 meters along the 4 meters along the horizontal direction. Along the horizontal direction. So determine now, determine the amount of work done. Determine the amount of work done by the boy. By the boy. Solution. Now we need to understand this question, then interpret it. And to interpret this question, we have to put it in diagrammatic. We have to use a diagrammatic representation to interpret this question. So, as we put it out, that will help us to quickly get the correct answer or solution to the question. Is that with the help of a rope inclined, with the help of a rope inclined at 30 degrees to the horizontal. So with the help of a rope inclined at 30 degrees to the horizontal, a boy exerted a 20 Newton pulling force at a desk and made it to move a distance of 4 meters along the horizontal direction. Now, with the help of a rope inclined at 30 degrees to the horizontal, let's assume inclined with the help of a rope inclined at 30 degrees to the horizontal. So, this is like inclined here, 30 degrees to the horizontal. A boy exerted a 20 Newton pulling force. A 20 Newton pulling force at a desk. At a desk, and made it to move a distance. Just like we have a desk, something like this here. So I just call this our desk. Now, with the help of a rope inclined at 30 degrees to the horizontal, a boy exerted a 20 degree Newton. So a 20 degree Newton. That the boy exerted 20 degree Newton. Then it has to put it and it has to come somewhere. So, and that must be somewhere here. Maybe this is the force that is exerted. 20 Newton. Putting a force at a desk and made it to move a distance. So of 4 meters. Of 4 meters. Now, so when it moved the load of 20 Newton, then the distance it moves is just 4 meters. 4 meters. Now, 4 meters along the horizontal line. Sorry, 4 meters along the horizontal line. That is somewhere here. Sorry. Along the horizontal line, 4 meters. Determine the amount of work done by the boy. So we are going to determine the amount of work done by the boy. Now to get this now, we know that work done normally is equal to force times distance. Force times distance. And our force is mass times acceleration. And our force is mass times acceleration. So, but here now, we are not dealing with that. There's an angle here. And with that, we are dividing, and we talk about this under angular velocity. So we talk about this under angular velocity. So when we talk about F cos theta, Fs cos theta, or F times S. So Fs cos theta, F times S. So it depends on how the question comes. Now, but because we're having an angle, so we must make use of Fs cos theta. We must use of Fs cos theta. Our force, our speed, and our theta. So with the help of a rope inclined at 30 degrees to the horizontal, a boy has started the 20 Newton pulling force. Our force is 20 Newton here right now. We have been giving force, but that is why we don't need to say we are dealing with a mass acceleration or something, blah, blah, blah. So in as much your force has been given in the question. So this will be equal to, our force is 20 Newton. Cos theta is 30 degrees. The question is, with the help of a rope inclined at 30 degrees to the horizontal, a boy has acted a 20 Newton pulling force at a depth and made it to move a distance of 4 meters along the horizontal direction. Determine the amount of work done by the boy. And this is the diagrammatic representation. So a rope inclined, the rope inclined at that 30 degrees to the horizontal. So it inclined at 30 degrees to the horizontal. So a boy has started a 20 Newton pulling force, 20 Newton pulling force at a depth and made it to move a distance of 4 meters. So along the horizontal. Now the formula I'm going to use Fs cos theta. We cannot use mass acceleration times a distance because our force has been given as a 20 Newton already. And that's why we say 20 times 4 cos, so 30 cos 30. Those students online. I don't know how we are going to get cos 30 now. So 20, I was going to be equal to 20 times 4 times cos 30. What is cos 30? 0.1, just 0.15, 1542, 410. 0.1543. So cos theta. Now, cos 30, I mean, okay. Now, we can now multiply this 2 times 4 times 0. 20 times 4 times 0.1543. What is the answer? 12 point, this is not 12.3. So joule. So this is our work done. This is the work done by the boy. So this is the work done by the boy. It's as simple as that. You all can look into it. Okay, let's write our parameter. So our angle is equal to 30 degrees. F is equal to 20. And this time is equal to 4 meters. That's our parameter. So with that, we can get our right answer. So I want you to get that so we can move to another calculation on that work. If you have all gotten what is on the board, then we can move on into another question. Move on to another question. So let's look into these examples. With this another example. The amount of work done by a crane, the amount of work done, the amount of work done by a crane, in lifting a 10,000 kg, a 10,000 kilogram car is estimated to be 3 millijoule. Okay. To what height is the car lifted? To what height is the car? Yeah.
Please, you have 9 minutes more.
Okay. Is the car lifted? So to what height is the car lifted? So we should take G to be equal to 10 meter. Take G to be equal to 10 meter per second square. So let's quickly look at the solution because of our time. Now, the amount of work done by a crane in lifting a 10,000 kilogram car is estimated to be 3 millijoule. So what height is the car lifted? Now, the first thing that we have to deal with is to convert this 3 millijoule back to joule. To convert this 3 millijoule back to joule. So when we convert this back to joule, then we can move on with our real work or calculation. So 3 millijoule will be equal to 3 times 1 million. What this means is that there is 1 million millijoule in 1 joule. So 3 millijoule will be equal to 3 times 1 million. So, and this will be equal to, and what that this will be equal to 3 million. But if you put it in index form, that will be 3 times 10 raised to the power 6 joule. So 3 times 10 raised to the power 3 joule. Now, so now that we have gotten the joule now, we can move on with our real solution now. So, and to find the work done, our work done is equal to force times distance. Force times distance. But they said the amount of work done by a crane in lifting a 10,000 kilogram car is estimated to be 3 millijoule. So there will be an opposing force of that car, because when the crane is trying to lift the car up, so there will be an opposing force that is of the car towards the crane. Now, the opposing force of the car, is equal to mg. And we know the mg, the mass of the car is 10,000 kilograms. The mass, opposite force of the car is in mg, and is equal to mg. So the weight of the car, so the mass of the car, the mass of the car is equal to 10,000 kilograms. I still have to wrap up the upper part of the question, so you can get enough space. Ready. Now, with this the question is solved as easy like that. Remember that our work done is equal to force times distance. And our force, now let's continue now. Mass of the car is equal to 10,000 kilograms. Now, what goes well force times distance? Force times S. Our force is equal to MA times S. Now, the mass of the car is equal to 10,000 kilograms times acceleration, which is what? 10 meters per second square, times what? The distance. So times the distance, which is not given. Now, we want to do this, this will be equal to 10,000 times 10. 10,000 times 10, the mass and the acceleration. And this will give us something like 10,000. Okay. This will give us 100,000. 100,000. Here are the force and distance. 10,000 times 10 meters per second square. So it's 100,000. And this is the force times the distance now. Where the problem is lying now. Now the distance moved. According to the question, let's look. The distance moves. A car is lifted to what height is the car lifted? Okay. To get the distance moved, which is the S. This should be equal to Sorry. So our distance moved. Okay, so the distance moved will be equal to the force applied. So to move the 3 millijoule that we converted, which is 3 times 10 raised to power 6. Force exerted and the applied force, sorry, and the applied force, which is 100,000 Newton. And before we can write the 100,000 Newton, we have to convert it back to